Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with chapter 6 of microwave engineering, a family of microwave bipolar transistors we are dealing with. The basic principles, the physical configuration, the various details we have gone through so far along with the power frequency limitations. Now we have recently dealt with the heterojunction type of the bipolar transistors useful for microwave applications here. So as in the previous video we have solved a recent problem here. Let us take another problem for another kind of heterojunction bipolar transistor. The problem statement is provided to us. It is an N-germanium G, P-gallium arsenide, N-gallium arsenide heterojunction transistor at 300 degree Kelvin has the following parameters. The parameters are denoted as Nd is equal to 5 into 10 raised to power 18 per centimeter cube. Na is equal to 6 into 10 raised to power 16 per centimeter cube. Tau suffix p is equal to 6 into 10 raised to power minus 6 seconds. V suffix e is equal to 1 volt. Capital A is equal to 2 into 10 raised to power minus 2 centimeter square. We are asked to make computations for, in the part A, the built-in voltage into the p-type gallium arsenide side. In the part B, the hole mobility. In the part C, the hole diffusion constant. D, the minority hole density into the N-type of the germanium region. In the part E, the minority electron density into the p-type of gallium arsenide region. In the part F, the hole diffusion length. In the G, the emitter junction current. So to see this problem statement, it is very clear that N-type germanium is the one type of the region, p-type gallium arsenide is the another type of the region, N-type gallium arsenide, this is another type of the region. So we have N, P and N. So this way the heterojunctions have been configured into the bipolar transistor here. So now we shall be first of all identifying what are the given details right from Nd to that of the capital A. So the first parameter Nd is nothing but the donor impurity. So here I mention the given details. So very first parameter is for donor density. Donor density into the N-type region of germanium it is. So here we have Nd is equal to 5 into 10 raised to power 18 per centimeter cube here. The next parameter is Na. So A stands for the acceptor density. So acceptor density is for the p-type of the gallium arsenide region denoted by Na with the value 6 into 10 raised to power 16 per centimeter cube. The next value is denoted as a measurement of time denoted by tau suffix p. It is nothing but the lifetime of the hole, hence I write whole lifetime. So whole lifetime is equal to 6 into 10 raised to power minus 6 second. So 6 microseconds the hole will be lasting into the semiconductor material. Now we have V suffix E. V suffix E is nothing but the bias voltage. It is the bias voltage at the emitter place, emitter junction. So VE is equal to 1. So it should be in terms of volts here. And the last portion, the last parameter we have, that is capital A. As you see the unit here, it is nothing but the cross-sectional area. So cross-section area, capital A is equal to 2 into 10 raised to power minus 2 centimeter square it is. Now we get back to the problem statement. We focus our attention to compute a built-in voltage into the p-type gallium arsenide side. So the built-in voltage for the p-type of the gallium arsenide side can be denoted by, here we write psi suffix 02 for the region. So it is computed by making the use of the Vt in negation. So I write the value minus 26 into 10 raised to power minus 3 it is, along with a natural logarithm for the ratio of concentrations here. So here the concentration for the acceptor impurity we are provided 6 into 10 raised to power 16. It will be divided by the intrinsic value 1.8 into 10 raised to power 6. So all the values are substituted and the corresponding answer for part A will be minus of 0.63. So as it is voltage, we measure it in terms of volts here. So I outline this answer. This is the required answer for part A. Now after finding the answer for part A, in the part B we compute the whole mobility. Now the whole mobility for the part B is given by mu suffix p here. Now for determination of the whole mobility, we make the use of the graph that we have used in the before problems of the chapter. So for the whole mobility determination, we get back to this chart here. The graph here is versus of the impurity concentration in terms of per centimeter cube with respect to the mobility values in terms of centimeter square per volt second here. So from the graph here, we determine the value of the whole mobility is equal to 400 in terms of centimeter square per volt second here. So this is the answer for part B. Now after completion of part B, we require the answer for the whole diffusion constant for part C. Now the whole diffusion constant for the part C we denote by capital D suffix P here, and it can be computed by making the multiplication of the mobility that just now we have determined, that is represented as mu suffix P along with Vt here. So it is a voltage. So substituting 400 in place of mu P and 26 into 10 raised to power minus 3 in place of Vt gives us the answer for D suffix P is equal to, the answer is 10.40 in terms of centimeters per second here. So I outline this answer 10.40 centimeter square per second. So after the hole diffusion constant, we require the minority hole density in the region of N-type germanium represented as the first region here. So for part D here, we make the use of the formula where we have the representations by P suffix N0 computed as the ratio of Ni square divided by Nd for the donor impurity here. So here we substitute the values. The numerator will be a square of 1.5 into 10 raised to power 10 here. So that is to be squared, and it is divided by the impurity concentration 5 into 10 raised to power 18 here. So the ratio gives us the answer 45 per centimeter cube. So this is the required P suffix N0, the minority electron density, as the answer for part D here. So after determination of the answer for part D, we require the next minority electron density in the region of p-type gallium arsenide region. So for determination of the answer for part E, here we represent N suffix P0 and we get it computed by the ratio as like before. So the numerator will be a square of the intrinsic concentration 1.8 into 10 raised to power 6, and it is divided by the impurity concentration 6 into 10 raised to power 16. The required answer we obtain as 5.4 into 10 raised to power minus 3 in terms of per centimeter cube. So I outline the required answer for part E here. Now after part E, we require the value of the whole diffusion length in the part F. Now the whole diffusion length for the part F can be denoted by capital L suffix P, and it is computed by taking the square root of the multiplication of tau P into the diffusion coefficient D suffix P here. So in the RHS, taking the square root for the values substituted, here we have the diffusion coefficient, and along with the lifetime of the hole here, it is 6 into 10 raised to power minus 6 microsecond it was. In multiplication to 10.40 we make it. So this computation gives us the answer, that is 7.90 into 10 raised to power minus 3 in terms of centimeters, as it is a length here. So I outline the required value as the answer for part F. Now after part F, in the last section, we require the value of the emitter junction current. The emitter junction current for the last portion, that it is G here, can be denoted by capital I. And the formulation used for computation, we have capital A into the electronic charge Q into the diffusion coefficient dP into Pn0 we have computed divided by L suffix P in multiplication to the difference of exponent of V by Vt minus 1 here. So we can make the substitutions as, for the A we put 2 into 10 raised to power minus 2 in multiplication to 1.6 into 10 raised to power minus 19 into 10.4 into 45 divided by, here we have 7.9 into 10 raised to power minus 3, and this all is in multiplication to the square bracket that has e to the power 1 divided by 26 into 10 raised to power minus 3. So 1 for VE and 26 into 10 raised to power minus 3 for Vt here. This is minus 1 here. So this gives the final answer 0.958. So as this is the current here, we measure it in terms of amperes. So I outline the required current value. So this way we are covered with the problem 2 for the heterojunction bipolar transistors. By the next lecture, we shall be addressing the brief introduction to the junction field effect transistors, that it is JFET, useful to work with the microwave engineering applications. I hope you enjoy the details with the microwave engineering. For more information and knowledge, you can subscribe to Ekeeda channel. Thank you.